In this video, we will be discussing game theory and how to find Nash equilibrium in both a simultaneous and sequential move game. Here we have a problem where we have two companies that are deciding whether or not they should build a new factory in the Midwest. And they have a game table of the following profits that depend on the decision both players make. And we want to find Nash equilibrium, the associated payouts, and any dominated or dominant strategies. So what game theory is all about is how decisions can lead to certain outcomes. And we're going to use game theory here to find our Nash equilibrium, or our most likely outcome, based on the decisions given to us, which are build and don't build. So what we need to do is we need to look at both players and use strategic foresight to find the decision of each player that would lead to the most likely outcome. So starting as player 1, and I'm going to use yellow to denote their decision, we're going to compare their profits between player 2's decisions, and based off of player 2's decision, player 1 will make a decision on what they want to do. So, since we're player 1, we're going to look left to right, since we're the role player, and we're going to compare player 2's build and don't build options with player 1's available options. So if player 2 builds, we look at the first number of 20 or 16 for player 1, because the first number is always player 1's payout, and the second number is always player 2's payout. And we compare the first two numbers in this column to see which decision player 1 would make. So 20 is higher than 16, so player 1 would choose build if player 2 was to choose build. Now if player 2 was to choose don't build a new factory, player 1 would compare the 13 and the 11 and see that 13 is the higher number, so we highlight that in yellow to show this is player 1's decision. So player 1 will always choose build no matter what in this scenario. So now that player 1 has found their most likely decision, player 2 is also going to make their decision based off of player 1's choices. Player 2 is also going to make their decision based off of player 1. So using strategic foresight, player 2 is going to look at their numbers, which are the second numbers in the pair, and compare their decision-making process based off of what player 1 does. So if player 1 builds, player 2 can decide to build or not build. And we would compare the 25 and 17. And we see that 25 is the higher number, so player 2 would choose build if player 1 was to build. Now if player 1 was to not build, player 2 would compare the 21 and the 15, and 21's the higher number, so player 2 would build if player 1 were to not build. So as a result, we can see our most likely outcome based off of both players' likely decisions. So our Nash equilibrium is build. Because this is our most likely outcome. As both players will always choose to build, it results in a Nash equilibrium of build. Note that Nash equilibrium is the strategies, or the decisions, not the numbers that we highlighted. The numbers that we highlight are our associated payouts. And our associated payouts are 20 for player 1 and 25 for player 2. So now we want to find any dominant or dominated strategies. And our dominant strategies are strategies that the player will always do no matter what. So if there's no reason not to choose this strategy, they will always pick this strategy, and that is their dominant strategy. Their dominated strategy is the opposite, as they will never choose this option, and therefore it can be eliminated from the decision-making process. So, as we saw before, neither player chose to don't build the factory. So, their dominated strategy would be don't build for both players. Now for the dominant strategy, we saw that both players would always build no matter what. So their dominant strategy would be to build for both. So, in a simultaneous game, this is what we would do to find our Nash equilibrium, our associated payouts, and our dominant and dominated strategies. Since we have looked at the simultaneous move game, let's now look at the sequential move game. So player 1 hears about player 2's strategy through the grapevine and prepares to make the first move. So our first mover is player 1 in this case, and we want to find the new Nash equilibrium and associated payouts, and we also want to figure out if there's a first mover's advantage from player 1 moving first. So for a sequential move game, we would take our game table and convert it into a game tree. So it forms a bit of a branching pathway here. So we have player 1, and they have two choices, or two decisions, where they can build or not build. And then player 2 has two decisions based off of player 1's decision. So player 2 can decide to build or don't build if player 1 builds, and player 2 can decide to build or not build if player 1 decides to not build. And each outcome has its own payout. And we want to see what the most likely outcome will be given that player 1 moves first. So what we want to do is we want to use strategic foresight to see what decisions are the most likely for player 2 to make, and then what decision player 1 will make based off of player 2's most likely decision. So what we want to do is we want to look at each branching pathway for player 1, so build and don't build, and we see that player 2 has two options from each pathway or decision. So if we look at the second number for the second player, or the player that moves second, which in this case is player 2, we want to compare which number is the most likely for them. So we want to compare which number looks better for player 2. So we see 25 and 17, and since 25 is a bigger number than 17, player 2 would build if player 1 were to build. And if we were to do the same for if player 1 was to not build, we see 21 and 15. So player 2 would choose to build in this situation, as 21 is a higher number. And based off of the elimination of the dominated strategy for player 2, or the decision that they will never do, in this case, which is don't build if player 1 were to build, and don't build if player 1 were to not build, and we compare which number for player 1, or the first number, or our first mover, would give player 1 the higher profit. So we see 20 is higher than 16, so player 1 is going to choose to build in this situation. So we get a Nash equilibrium of build again. So our Nash equilibrium is our most likely outcome in this situation, given that both players are making rational decisions. And we see that there is an associated payout of 20, 25. And we want to see if there's a first mover's advantage. And if we look back at our original Nash equilibrium for the simultaneous game and compare it to our Nash equilibrium of the sequential move game, we have the exact same Nash equilibrium. So in this case, both a simultaneous and sequential move game lead to the same outcome, so there is not a first mover's advantage because the first mover does not gain anything more from moving first in this case. That will conclude this video on game theory.